So in this video, we're going to talk about section 12.4 and 12.4.1, which is a basic overview of estimation of population parameters and properties of these estimators. So we've gone over section 12.1 and to 12.3, 12.2, 12.3 really fast, but 12.1 is basically estimating the population mean using the sample mean. So this section has to do with statistical inference from sample information. We basically, because some problems are too hard to solve because there's too many things in a population, right? And what we want to estimate is a population parameter. So the population parameter is a characteristic of an entire population. We usually label it data. Such population parameters are population mean, standard deviation, and proportion, population proportion. A statistic is a measure that's computed from a sample of a population to describe characteristics of that sample. And in fact, that statistic, which is also called a rule, is used to approximate or estimate the population parameter, and it's called the point estimator for theta, and it's denoted by theta bar. Remember, theta is the population parameter. So theta bar will be the estimate of the two population parameters. A numerical value that's assumed by this statistic or point estimator when evaluated for a given sample is called a point estimate for theta. So for example, to estimate the population mean, we use the statistic or point estimator of the sample mean. To estimate the standard deviation of the population, we use the sample standard deviation. To estimate the population variance, we use the sample variance. To estimate the population proportion, we estimate by the sample proportion. So here, for example, suppose an investment manager who manages 50 portfolios wants information on how well his portfolios are doing. So he doesn't want to have all the information on all his portfolios. So he just takes a sample of 10 of them, for example, whose earnings are in the thousands per year, or 95, 67 here. So what's a point estimator of the true population mean? Well, in this case, X bar is just you add up all the earnings of the 10 portfolios all the way to 79, and then we divide by 10 of them. And you get 74.9. The point estimator for the sample variance of the two population variance, right, sigma squared, this is the mean, is the sample variance. So it's x minus x bar squared, all divided by n minus 1. So in this case, it's like 95 minus 74.9 squared, all up to the last number, 79 minus 74.9 squared, divided by 10 minus 1. Remember, it's a 10 minus 1. Be careful. This is the sample variance. Sample variance. So then the answer would be whatever it is. Okay. Now, estimator, the bar is unbiased estimator, if and only if the expectation of the sample distribution, or the mean of the sample distribution, is equal to the actual population parameter. For example, in fact, the sample mean distribution is an unbiased estimator, or the sample mean statistic is an unbiased estimator for the population mean, since sample distribution has a mean or expected value equal to the population mean. And we briefly went over 12.2, 12.3, but we know that the sample proportion statistic with sample distribution of the sample proportions, the mean or expected value of the sample proportion distribution is just equal to the population proportion. And similarly, the sample variance statistic is an unbiased estimator for the population variance. It's the mean or expected value of the sample variance distribution. It's given by the population variance. And we say that the point estimators is consistent if, as n goes to infinity, the variance, or remember, of the sample distribution goes to 0. So in fact, the sample mean is a consistent estimator for the population mean because remember the variance goes to 0 as n approaches infinity.